Dear students, we will discuss about the tolerance stack analysis in this session. I have shown three components on the sheet: a shaft, then a cylindrical component and another cylindrical component. I want to assemble these three components, as shown in this figure. On assembling these three components, I am going to apply a nut and washer so that when I tighten the nut, these two parts can be firmly fixed against the shaft. I want to find out the play between this face of the component and this face of the shaft. This play I want to find out using Surfit law and later using normal law. To find out the play between this face and this face, I am drawing a dimension loop over the assembly drawing. For drawing the dimension loop, let me take this face as the origin. From the origin point, whenever I move towards the right side, let me take a convention of plus. Whenever I move towards the left side, I take the convention of minus. Now I am starting from this origin point. I am moving over the dimension A. The dimension A is occurring on this first component. Then from here I am moving over dimension B. The dimension B is occurring on the second component. Then I am moving over the play. The play is between the end of this face and this face of the shaft. Then I am moving over to the dimension C, which is occurring on the shaft. Since I have come back to the initial position again, the total length will become 0. Let me explain again. Dimension A, since I have moved towards the positive side, plus A. Then from A to B, since I have moved again towards the right side, I have taken plus B. Then from here I have moved to this face of the shaft. Since I have moved towards left side, minus play. From here I have moved on to the shoulder of the shaft, C. The C is negative because I have moved towards the left side of the convention. Minus C is equal to 0. Why I am putting 0 here is I have started from a point, using a loop. I again come back to the initial point. So the sum of these dimensions should be equal to 0 since I have come back to the initial position again. So from this, A plus B minus play minus C is equal to 0. This is the dimension loop I am getting. From this, the play is found out as play is equal to A plus B minus C. Now the dimension A, dimension B, dimension C has to be substituted here. So before we substitute the dimensions, it is better to convert these dimensions into equal bilateral form. 20 minus 0, 0 minus 0.6 is occurring on the first component. That is converted into equal bilateral form as 19.97 plus or minus 0.03. Second dimension is 35 minus 0, 0 minus 0.4 is converted into B bar, 34.98 plus or minus 0.2. In the equal bilateral form. Similarly, dimension C is the length on the shaft. It is already in the equal bilateral form. Let me take the C as 54.5 plus or minus 0.1. So having converted all the three dimensions into equal bilateral form, I am applying this on this equation. So A is 19.97, 34.8 minus 54.5. The sum comes to 0.45. Okay, what we understand is, on assembling these three parts, the play, okay, is found out to be 0.45. The mean value of the play is found out to be 0.45. This 0.45 is the play. Okay, it is not constant for all the assemblies. It depends upon the individual dimension attained by each and every assembly. Okay, in one of the assembly, okay, the shaft size may be 54.5. In another assembly, okay, the shaft size may be 54.6. The another assembly, the shaft size may be 54.4. So depending upon the individual dimensions of a particular assembly, okay, the play will vary. So this the mean value of the play is 0.45. Okay, from the mean value, how much it varies. We are going to apply the normal law. Sorry, we are first initially we are going to apply the Surfit law to find the variation about the mean play. So the variation about the mean play is given by A plus B plus C. So these are the three dimensions which are involved in finding the play. Okay, using the loop we have found out. Okay, play is given by A plus B minus C. So these three dimensions is involved in finding the play. So the tolerance of these three dimensions is small a, small b, small c. So the value of small a, small b, small c is found here. Okay, we have converted the dimensions into equal bilateral form. So small a is not 3, small b is not 2, and small c is 0.1. Adding these three, 0.03 plus 0.02 plus 0.1, you are getting the variation about the mean play as 0.15. So finally, the play is found as 0.45 plus or minus 0.15 as per the Surfit law. Okay, it is varying from 0.32 to 0.6. So this is the how we are going to find the tolerance stack, using the Surfit law. So the play finally is found out as varying from 0.3 to 0.6 from assembly to assembly. In one assembly it may be 0.3, in another assembly it may be 0.4, in another assembly it may be 0.5. So the play varies from assembly to assembly. It is found to vary between 0.3 to 0.6 by applying the Surfit law. The play which is found as varying between 0.3 to 0.6 is found by assuming that each and every dimensions follow uniform frequency distribution. We can able to find the answer, the play, by applying another law called normal law. The normal law assumes that each and every dimensions follow normal frequency distribution. Okay, we have known that the play is affected by dimension A, dimension B, dimension C. Dimension A is normally distributed. Similarly, dimension B and dimension C are all normally distributed. So we have to find the play as per normal law as a second case. So the normal distribution as mean and standard deviation. The mean value already found out. The mean value of the first dimension is 19.97. The mean value of second dimension is 34.98. Mean value of third dimension is 54.5. How to find the standard deviation? Now we assume that the normal curve is exactly fitted between the upper specification limit of 20, lower specification limit of 19.94 as far as the first dimension is concerned. In that case, the distance between the USL and the mean is 3 sigma 1. So 3 sigma 1 is equal to 0.03. So from that we can find the sigma 1 as 0.01. So the first dimension has got a mean value of 19.97 and a standard deviation of 0.01. Second dimension, mean value of 34.98 and the sigma is found as 3 sigma 2 is equal to 0.02. From that we find the sigma 2 as 0.00667. Third dimension is having mean of 54.5 and standard deviation of 0.0333. So from this I can able to find the answer by normal law. So the mean value of the play is same as that of Surfit law, A plus B minus C. So the mean value of dimension A is 19.97 plus 34.98 minus 54.5, you get 0.45 as the mean value of the play as per normal also. But the variation about the mean play, to find out the variation about the mean play, first we have to find out the standard deviation of the resulting distribution. So now this is the distribution of the play, the mean value mu A and standard deviation sigma A. So we have to find the sigma A using the applying the normal law. Sigma A squared is equal to sum of the sigma 1 squared, sigma 2 squared, sigma 3 squared. As per normal law, we find the standard deviation of the resulting distribution as the sum of the square of the standard deviation of the individual dimensions. So from this, 0.1 square plus 0.667 square plus 0.33 square, we get as sigma A as 0.034543. From the sigma A, how to find the play? The variation about the mean play is equal to 3 sigma A. So we find that the play is 0.45, mean value is 0.45 plus or minus 3 sigma A. So 0.45 plus or minus 3 sigma A comes around 0.1. So this is the answer we arrived as per the normal law. Let us compare this answer with the Surfit law answer. As per Surfit law, we got the play as 0.45 plus or minus 0.15. As per the normal law, we got the answer as 0.45 plus or minus 0.1. For the same play, we got the answer as per the Surfit law as 0.45 plus or minus 0.15, as per the normal law as 0.45 plus or minus. Instead of finding the standard deviation of individual dimensions, sigma 1, sigma 2, sigma 3, then applying in the formula sigma A squared equal to sigma 1 squared plus sigma 2 squared plus sigma 3 squared, we can directly find the answer using this formula. When I want to find out the resulting dimension using normal law, you can apply this formula. UA is the mean value of the resulting dimension, plus or minus small ua is the variation about the mean dimension, is found as ua plus or minus square root of u1 squared plus u2 squared plus u3 squared, where u1, u2, u3 are the tolerance of the dimension number 1, dimension number 2, dimension number 3. So here the tolerances are 0.03, 0.02, 0.1. So you can check that in the drawing. See here, the tolerance of the dimension A is 0.03, dimension B is 0.02, and dimension C is 0.1. So when I apply that in the formula, the tolerance of the resulting dimension is nothing but square root of the sum of the individual dimension tolerances. So I got the same answer as 0.45 plus or minus 0.1.